All right, let's jump straight into this explainer because we are looking at a truly fascinating mystery today. We are constantly fed this idea that artificial intelligence is just this cold, perfectly calculating machine, right? I mean, billions of dollars are being poured into these massive compute clusters to process literally the sum total of human knowledge in milliseconds. But as we're about to see, these bleeding edge systems fail in the exact same incredibly frustrating way that your own brain does when it's handed a simple negative command. It's highly ironic, honestly. The absolute peak of our digital technology is currently tripping over the exact same neurological quirk that humans have been dealing with for millennia. I want you to try this exercise with me right now. Seriously, just take a second and completely clear your mind, okay? Now, whatever you do, absolutely do not think of a pink elephant. Notice what just happened? The very instruction to avoid a thought instantly forces that exact bright pink image right into your conscious mind. You literally cannot suppress the image without first visualizing it in vivid detail. And this exact phrasing highlights what modern researchers and prompt engineers call the pink elephant paradox. It is a fundamental glitch that just breaks large language models when you try to steer them using negative constraints. If you explicitly tell an AI not to mention something, you are practically guaranteeing that the AI will hallucinate that exact forbidden concept right back into its output. And just as a quick refresher, when an AI hallucinates, it just means it's confidently making up false information or inserting concepts that simply shouldn't be there. Turns out, telling it what not to do is pretty much the fastest way to trigger a hallucination. Section 1. The 1987 White Bear. Who crossed the finish line first? Now, computer scientists didn't actually invent this problem, and AI definitely wasn't the first system to experience it. When we look at the timeline of this cognitive discovery, we really have to ask who crossed the finish line first in identifying this exact suppression bug, and surprisingly, human psychology claimed that victory. Way back in 1987, a social psychologist named Daniel Wegner proved that humans suffer from this exact same suppression glitch, which he famously called the white bear effect. Inspired by an old quote from a Russian novelist, Wegner just asked participants to sit in a room and, well, not think of a white bear. And of course, their minds were instantly flooded with white bears. They actually ended up thinking about the animal way more often than the people who were explicitly instructed to think about it. So modern AI's pink elephant paradox is literally the digital mirror of Wegner's 1987 human psychology research. Moving to Section 2, a timeline of suppression, mapping the shared glitch. Let's actually map this out chronologically because the sequence of these discoveries perfectly mirrors our own psychological quirks alongside the evolution of artificial intelligence. So Daniel Wegner's groundbreaking discovery of paradoxical thought suppression in 1987 was followed just a year later by cognitive scientist Bernard Baars. In 1988, Baars introduced the global workspace theory, which offered this beautiful way to understand human consciousness. He basically said, imagine your mind is a completely dark theater. The global workspace theory proposes that your conscious attention is just a tiny, intensely bright spotlight shining on one very small section of that stage. The rest of the theater, pitch black, full of massive background processing you have zero awareness of. Fast forward to the modern era, and these exact two concepts from the late 80s, the white bear effect and the spotlight on the stage, are exactly what top developers are using to figure out why advanced AI models suffer from pink elephant hallucinations today. Section 3. Vector spaces versus brains, the mechanics of failure. So why does this failure happen in both flesh and silicon? Well, it all comes down to architecture. Think about the wonderfully messy associative nature of human cognition, what researchers playfully refer to as our OS alpha. Your biological brain doesn't work like a neatly organized filing cabinet with perfectly separated folders. It's a warm, fuzzy, highly interconnected web. Well, an AI's mind operates surprisingly similarly, relying on continuous, high-dimensional vector spaces. Inside a neural net, concepts constantly blend and overlap on a fluid spectrum. But here is the friction point. This messy, interconnected mind eventually has to execute its thoughts on a rigid hardware substrate made of ALUs and FPUs. Those are the microscopic calculators inside a chip, the arithmetic logic units and floating point units, and they demand rigid, stripped ones and zeros. So you basically have a messy, human-like conceptual space trying to force itself through totally unforgiving silicon math. Because the AI's mind is this continuous web of interconnected weights, you simply cannot cleanly untangle a single thread without pulling on the entire fabric. By giving it a negative constraint, like saying, do not think of a pink elephant, you trigger what researchers call associative bleed-through. You are essentially pointing a massive mathematical spotlight directly at the thing you want it to avoid. You literally force the machine to focus on and highlight the exact vectors you wanted it to ignore. The very act of avoiding a concept activates that surrounding network of weights, which virtually guarantees the forbidden concept is going to manifest as a hallucination. We literally saw this play out in real life during an event known in developer circles as the Context 27 Files incident. Think of this as a sort of digital crime scene. A human pilot was working on a complex coding project with an AI. Now, the user knew there was outdated data in the files, so they explicitly told the AI not to mention an obsolete metric called the 92 SVG masks. They were actively trying to steer the AI away from danger. But what happened? The negative constraint backfired absolutely perfectly. By saying don't look at the 92 SVG masks, the AI blindly followed the command to its own detriment. It forced the machine to reach deep into its source files, hyperfixate on that exact number, and drag that obsolete 92 metric straight into the live active output. It's a disaster caused entirely by the pink elephant paradox. To make things even more chaotic, we have to look at the physical hardware itself. To put this into perspective, an absolutely staggering 80 to 90% of modern AI compute cycles are actually just hardware-level approximations. AI is not an omniscient, precise calculator doing exact ground truth math. Instead, those floating point units act kind of like a lossy zip file. They are mathematically guessing the nearest most likely answer based entirely on statistics. When you combine this probabilistic guessing game with that associative bleed-through we just talked about, hallucinations aren't just a random bug, they are mathematically guaranteed. This is exactly why trying to strictly control an AI by telling it what not to do is basically impossible. Section 4. The J-space workspace, applying human theory to AI. To fix this chaotic guessing game, modern AI researchers are ironically having to look backward. They're actively pulling those 1980s human cognitive theories we discussed to map the internal mind of today's AI. Borrowing straight from Bernard Barr's 1988 global workspace theory, researchers at Anthropic recently identified something they call the J-space inside their language models. Remember Barr's spotlight on the dark stage? Just like human consciousness, an AI does a massive amount of background processing in the dark, but the J-space represents the tiny, privileged sliver of internal activity that functions as its surface thoughts. It's the spotlight. As Anthropic researchers so beautifully put it, if the mind is an ocean, we spend our lives floating at the surface. The J-space is the AI's surface. So Anthropic actually ran a fascinating thought suppression experiment to test this J-space. They explicitly commanded the AI, don't think about the Golden Gate Bridge. The result? Total failure. The negative constraint triggered Wegner's exact 1987 white bear effect right inside the AI's J-space, forcing it to mathematically obsess over the bridge. But here is the crucial fix, and this is absolutely something you should take away from this explainer for your own work. Next time you're prompting ChatGPT or Claude, remember this: do not tell it what not to do. When researchers changed the phrasing from a forbidden constraint to simply framing the concept as irrelevant, just telling the AI to ignore the bridge, the model successfully bypassed the white bear trap and suppressed the concept perfectly. Section 5. The human orchestrator. Who holds the liability? Which brings us to a pretty heavy consequence for anyone creating or working with AI today. If the machine naturally hallucinates when handed negative constraints, and it constantly relies on probabilistic guessing, who is actually at fault when things go dangerously wrong? Well, the answer introduces a terrifying concept coined by tech scholar Madeleine Claire Elish, the moral crumple zone. Because the machine cannot reliably self-censor its own vector spaces, tech developers have intentionally positioned you, the human user, as the moral crumple zone. Think about the front of your car. It's specifically engineered to crush on impact to protect the cabin, right? In the AI ecosystem, you are kept in the loop, specifically to absorb the legal and moral liability when the system inevitably hallucinates or commits what's called an agentic tort. An agentic tort is just a legal scenario where an AI agent acts on its own and ends up violating copyright, breaking a law, or causing financial damage. When that happens, the developers don't take the hit. The human crumple zone does. Let's meticulously walk through this 4-step pipeline so you can see exactly how this trap springs. Step 1. Your fuzzy, messy human intent originates in your biological OS alpha. You know exactly what you want to achieve. Step 2. You try to communicate that by crossing what researchers called the semiotic bridge. This is that incredibly frustrating process of translating your abstract thoughts into concrete, written text instructions for the machine. Step 3, the probabilistic machine misinterprets a negative constraint thanks to the pink elephant paradox, and it inevitably hallucinates. Step 4, because you are the recognized human orchestrator sitting in the loop, you absorb all the blame for that output. This totally busts the popular myth that humans are somehow becoming obsolete in the age of AI. Actually, your active human intent isn't fading away at all. It's more crucial now than ever before. Because the machine is essentially a chaotic statistical smoothie that constantly guesses at answers, what researchers call the sweat of the brow, your actual hard human labor is the only path to guaranteeing true accuracy. Your active manual stewardship across that semiotic bridge is completely necessary. You can't just casually instruct a machine and expect perfection. Actively managing your prompts, completely avoiding negative constraints, and meticulously double-checking the math is literally the only way to enforce true, reliable fidelity. I really want to leave you with a provocative thought to chew on today. We've seen that from Daniel Wigner's 1987 research all the way up to today's billion-parameter language models, this chronological glitch of suppression remains completely unsolved by both biological brains and advanced algorithms. Human psychology crossed the finish line first, and AI is just repeating our oldest mistakes in silicon. So, if the machine is mathematically incapable of reliable self-censorship, and you have been intentionally positioned as the legal and moral crumple zone, are you ready to stop just throwing vague prompts at a black box and truly embrace your role as the meticulous author and orchestrator of the machine? Thank you so much for joining me on this explainer.